Hi, welcome to week 12 of the course Privacy and Security in Online Social Media. This is the part 1 where, continuing thematically from the previous week, we'll try to look at some interesting papers which have some thematic relation to whatever we've been studying over the last 8 to 10 weeks, right? Tying this back to what we learned or what we saw in week 10, right? The ethics, bias, and all these sort of discussions with social media data, it's very important to consider all of that as well. And if you remember, this is one of the slides from week 10 where we were talking about this whole taxonomy of how biases come from, how biases manifest, and how what do these biases affect as well, right? So if you remember, we were talking about biases at source. If Twitter as a platform itself is biased, it can sort of manifest into different types of biases in user behavior, and then in turn it also actually reduces the validity of your research, and it sort of gets hard for you to defend your own research. So for today's session, the first part, we'll be focusing on how do these biases emerge, especially looking at Twitter data, because in the broader context we want to study biases in social data research. Then we also want to see how these biases affect behavioral biases, right? We want to do a deep dive into a specific paper which sort of looks into how Twitter as a platform affects the biases in the behavior of its users, right? So if you remember, a few years back, in November 2017, Twitter doubled the character limit of its tweets from 140 characters to 280 characters. Previously, it was only 140 characters. If you went beyond that limit, you will not be able to tweet in the same tweet. The Twitter allowed you to construct Twitter threads. So 140 character tweet 1, 140 character tweet 2, and so on. But in November 2017, Twitter immediately doubled the character limit of its tweets, and the motivation behind this was done to soothe the user's need to cram content in 140 characters. I think all of us have felt this as well. If we want to try to tweet a longer form content, it becomes very hard for us to tweet it and cram all the content in just one single tweet. So if you see this specific tweet here, you have Jack Dorsey, who was the CEO at that time of Twitter, and he says that this is a very small change but very big move for Twitter as a platform, because till that point in time, Twitter only allowed 140 characters in tweets, which was in turn motivated by the 160 character SMS limits of Airtel, Vodafone networks, right? And I'll come to the reasoning behind why 280 or 140 character limit as the motivation behind this study. And so this is one platform design that we have no control over, right? We do not have control over how many characters Twitter allows us to tweet about. And in this session, we want to look into specifically how this character limit manifests into certain specific characteristics or behaviors or biases in how users handle the platform and how users deal with the platform, right? So Twitter actually conducted an internal study and released this blog post, and it was hypothesized that users are in need of cramming the content in the 140 character limit, and it was discouraging the users to not tweet. Because if I want to quickly tweet something and if I see that okay, it's beyond 140 characters limit, I do not want to spend more of my time on reducing the content or adding more tweets to the same thread. So Twitter then in November 2017 came up with this blog post that you can see the link of here, and they go into mathematical modeling of how they came about this new 280 character limit, which we'll come to in the later slides, right? So specifically for this session, we want to look into this recent paper from CSEW forum, which works on social computing works and so on. So this paper, anticipated versus actual effects of platform design change, a case study of Twitter's character limit, right? So as I said, the broader context, Twitter changed the character limit, and it is a very specific platform design. Users do not have any control over it. And if you look back into the into this figure, right? We want to see how biases at the source, at the Twitter API level, how they inform the behavior of the users. And this is very well situated in this paper, and we will do a deep dive in today's session on this paper. So this paper was interested in looking at, okay, Twitter changed the API in 2017. How does this change affect the users? How does this change affect the platform as a whole? And how does it modify the estimates made by the researchers in Twitter, right? So if you look at the research questions asked by the Twitter researchers, they say that, did the introduction of 280 character limit change any user behavior? That they were anticipating already, which we'll also dive into a lot more details in the later sessions. So Twitter conducted a mathematical modeling of how many users would fall into this character limit, which will again come into the later slides. But so the main research question this paper was investigating was, after introducing this 280 character limit, after expanding the 140 character older limit to 280, do users behave differently? If they do so, how do they behave differently, right? And Twitter's hope in this platform specific design change was that users will not need to cram a lot of content anymore, because again, as I showed in the last slide, cramming content led to a lot of users not even tweeting about stuff. Coming to specifics, they had 3 sub research questions, RQ1, 2 and 3. One is the gaps between predictions made by Twitter and emerging user behavior, how users are actually behaving once the change was done, and by change I mean the expanding the character limit. The research question 2 is concerning how does it affect different languages. So almost all of us tweet in English, but there are a lot of people who tweet in their native languages, right? European language, Indian languages, Hindi, Urdu, Tamil, Telugu and so on. The third question is more of a research platform estimate design question, where they want to see if the questions asked by the Twitter researchers hold up pretty well even right now. Fluidity of counterfactual estimates, right? So there were some estimates or predictions made by the Twitter researchers based on which they expanded the character limit to 140 to 280, and they want to test in RQ3 if that even makes sense, right? We'll come to all of these in a minute. So concerning the data used by the researchers of this paper, they collected the public dump of 1% sample tweets from the sample API between the period 1st January to 31st October 2019. And if you see, if you read in the highlighted screenshot, they only concern original tweets. They discard the retweets because, again, if you look into the biases that these platforms can manifest, redundancy was one of those biases we read about, right? Concerning the multilinguality of the data, they were looking into 23 languages, biggest languages on Twitter. The curious or the important thing to note here is that Twitter deliberately did not expand the character limit for 3 specific languages: Japanese, Korean and Chinese. This was because, based on previous literature and based on previous research, it is already established that these 3 languages, they have an extensive vocabulary and they do not need a lot of space to write a long form content, right? So let's look into how the data looks like, right? So if, as you can see, this is the Twitter data statistics. The A part of the figure is the languages, a number of original tweets in each language, and the color coding is blue languages are where the change was not implemented, and all the other languages orange colored where the change was implemented: English, Portuguese, Spanish and so on. So this is just the frequency based analysis. The more interesting plot here is the B part of the plot, where you can see the histograms, and they've nicely sort of given the date. 2017-11 is the time when the switch happened. So in all the subsequent slides, the switch will refer to the switch or the expansion of 140 character limit to the 280 character limit. And as you can see, they have a very curious peak around 140 characters till the switch happened, and then as soon as the switch happened, a lot of people started tweeting beyond the 140 character limit, and we'll conduct all of our analysis on this data, which becomes more and more interesting as we go into a bit more detail. Right. So coming to again a language specific analysis of the data set. We see the this figure shows you the histograms or the tweet length distributions before and after the switch happened. The red line indicates the histogram or the distribution of character lengths in the tweets before the switch happened, and the blue line plots the switch once the switch happened, right? So you have Hindi, Urdu, Persian, and they are ordered based on the largest prevalence on their frequency usage, right? So as you can see, there is a huge sharp rise in the distribution in the red plots, because before there was 140 character limit and all the people just stopped at 140. They did not have any way to go beyond that character limit, and so they had to cram a lot of content in. So the authors based their analysis on this hypothesis that this red line indicates that the majority of the content is being crammed in this 140 character limit, because the histogram looks like that. And then you also see the blue line on the other hand, where the blue line represents your tweet length distributions across all these languages after the switch happened, after the character limits were expanded to 280 characters. And you see the plot is much more uniformly distributed, it's much more normalized, and so on, right? So let's dive a bit more into in depth of how Twitter chose the specific character limit of 280. It wasn't just an arbitrary choice of let's just double the 140 character limit to 280, right? So taken again from the paper that the authors wrote, they say that based on the distributions that we just saw, right, these distributions follow a sort of log normal distribution, which is very similar to a normal distribution. The only difference is it follows a logarithmic plot instead of a standard Gaussian plot, and all the x-axis values get shifted to the positive side because you cannot have negative logarithms, right? The second thing that they observed is the empirical distribution, basically. So log normal is the theoretical distribution. You can fit a distribution based on your data set, and this would be your theoretical estimate of based on mean, mode, median, and these statistics. How does your data represent a theoretical distribution? But the second observation is much more interesting, where they say that the empirical distribution of tweet length, right, it follows log normal distribution till, let's say, 120 character limit, but as soon as you go near the 140 character limit, it deviates from the original distribution, because a lot of users are trying to squeeze their messages into the 140 character limit. And so we'll come to these two terms, size of cramming and size of runover, in a couple of minutes, but I want to highlight this specific line from the original authors, right? This is the whole motivation behind conducting this study. 9% of English tweets and only 0.4% of Japanese tweets do not make it under 140 characters. So if you want to improve or increase the character limit such that 99% of English tweets are able to tweet in the same tweet, then you have 274 characters, and this is just a heuristic that the authors used. We'll, in the subsequent slides, we'll look into a bit more mathematical details of how it happened, right? So the plot that you see in the left hand side, you see the log normal distribution as I was talking about. The solid black line is your histogram based on your dataset frequencies. The dotted black line is your fitted log normal distribution. As I was talking about, the black line is your empirical data based on the dataset that the 1% sample that you've downloaded from Twitter API. The dotted line in turn represents the theoretical distribution based on the statistics of this data. And as you can see, it follows a very theoretical Gaussian type distribution, but the real data sort of diverges and suddenly it shoots up to 140 character limit, because as we've already established, as you go near the 140 character limit, the users tend to squeeze or cram a lot of content in, and it deviates from the theoretical log normal distribution. The interesting thing here to look into is the authors have described these two regions of interest, right? You see a purple region and then you see a blue region, right? The blue region is cramming, the purple region is the size of runover. We'll come to the definitions of these as well. So blue is the size of cramming, where you want to see how much the theoretical distribution and the empirical distribution is deviating from each other, that area gives you the amount of cramming, right? So the authors have also mentioned cramming measures people's attempts to squeeze a lot of their tweets within the enforced character limit. Pretty intuitive, pretty understandable, right? The second part is more interesting, the run over, where this current research is situated in, right? The purple part, where you want to see so run over, the purple part captures the fraction of tweets that would be impacted by any hypothetical character limit. So if you want to increase your character limit to this dotted gray line, right, which is marked as hypothetical character limit, this purple region gives you the amount of the fraction of tweets that can be fit into this new character limit, this hypothetically new counterfactual character limit, which in our case, as we'll see later on, was 280. Right, so this was the theoretical or mathematical modeling of how Twitter chose the new character limit of 280, because as I already said that 140 was before, and based on the cramming and run over analysis, they saw that 99% of English tweets can be fit into 274 character limit. So why not just do a whole round off to it, and 280 was chosen by Twitter researchers in 2017. Right. So this is the second part where we move on to the results of the paper, and the slides mention each specific research question that we saw in one of the earlier slides, and the plots sort of give you the analysis that the researchers made answering those research questions. So the broader hypothesis was, okay, Twitter changed the character limit from 140 to 280. What is the impact of this change in character limit, right? And if you played around with Twitter API, you must have also observed, right, that it also gives you a lot of meta information, like whether the tweet was made from a mobile, whether the tweet was made from web, where the location of the user was, the language of the tweet, and so on. So coming back to it, the first research question was, the researchers wanted to analyze the gaps between predictions made by the Twitter engineering team and how users were actually behaving on the Twitter platform. And the very surprising thing that you will immediately see, right, is that the left hand side of the plot, the figure 4, gives you the estimates of, so the blue part is how the tweets were distributed, or tweets were being made each day before the character limit was expanded to 280. The gray part is the regression modeling or prediction based on this, but the blue part, the lower half, right, this is the part where what actually happened, how users were actually tweeting about stuff, right? And as you can see, there is a huge gap in the web part as compared to the mobile part. The mobile part was still more or less following the theoretical distribution, but in web, and the intuition for web is that if I'm on my laptop, right, if any of you are tweeting on your laptop or writing something on your laptop, you are more tending towards tweeting or writing a longer form content as compared to on mobile, where you would prefer tweeting short form content, just quickly you want to type something, right? So this plot basically tells you that immediately after the switch happened, the fraction of tweets that, so people now got to know that, okay, the Twitter character limit is expanded from 140, and they started expanding their character limit. They started posting a lot more longer form content, right? And then the authors have nicely summarized it into this text from the paper, where they say that on web there was 50% less cramming as compared to on mobile devices, and which basically tells you, right, that cramming is a smaller problem on mobile devices in general, because mobile devices generally are built for short form content, WhatsApp chats, small tweets, and so on, right? So the mathematical modeling that we've seen till now just talks about how users actually behaved versus what were the predictions made by the Twitter engineers, right? And what we saw was the modeling approach underestimated the fraction of tweets that would be longer than the 140 character limit. So Twitter engineers had predicted that once we expand the character limit from 140 to 280, a lot of users will not cram their content in 140 and they'll just go beyond, let's say, 160, 180. But what they observed surprisingly was now people have started cramming content into 280 character limits, right? Which is again counterintuitive and sort of goes against the principles of why Twitter wanted to expand this limit. So again, some interesting analysis that came out of this study were we've already seen how the user behavior is changing, but can we also look into the linguistic styles of this cramming of content? Can we see if tweets that were being crammed more towards 140 or now the new limit of 280, do they have some syntactic patterns? Do they have some semantic patterns and so on, right? So they, again, this slide just basically tells you they use LIWC, which we've already established is a standard NLP modeling toolkit, which gives you these part of speech tags and adverbs, which words are nouns, how many nouns were there in the tweet, how many adverbs, articles, conjunctions and so on. And the very interesting thing here to look into is, if you look into this plot, right, before and after the switch, you'll observe that a lot of this content that was removed from the crammed content, that was removed from tweets just nearing the character limit, they removed swear words, they removed spoken categories, they removed non-fluencies, fillers and articles, right, which are non-essential, which you can remove in your everyday language, but still you can communicate your broader meaning, which makes sense, right? If you're forced to limit yourself, your tweet to 140 or 280 characters, you can remove conjunctions, you can remove filler words, you can remove some stop words, right, while still communicating your broader idea. The interesting thing to note here again is, contrary to what Twitter engineers had believed, after the switch happened, if you look into the B part of the figure, right, even 280 character limit observed a lot of people cramming their content, but instead of 140, now a lot of people were cramming their content in 280 character limit. And again, a lot of people were removing fillers, accents, adverbs, conjunctions, basically the non-essential parts of speech. And what you can see from this graph is that no gaps were observed for verbs and negations, which are very essential to what you want to communicate on Twitter or in any language, right? So similar thing, again, still in the realm of syntactic indicators, they saw that they removed the users who were cramming a lot of their content into the character limit. They removed these syntactic indicators like I, he, she, they, we, because again, they are non-informative, but you can still sort of communicate the broader idea that you want to look into. The second part was the semantic indicator. So now we've seen, we've established two things, right? Once Twitter expanded the tweet limit, character limit from 140 to 280, contrary to what they had observed, what they wanted to predict, that users would stop cramming their content into 140 characters, users just started cramming their content in the new character limit of 280. The second thing we observed was the linguistic style or the linguistic properties also play a very important role, where you remove, if you are forced in a length constraint, if I say to you, right, write an essay in 1,000 words, you are forced to write something in specifically 1,000 words, and you would sort of remove non-informative, non-functional words, and that's what we've established till now. But let's look into what are the topics being talked about in the tweets which are sort of within the character limit and which were cramming their content a lot. So as you can see, the authors observed that a lot of topics like work, money, achievement, death and religion, these are less frequent on the 140 character limit as compared to topics like personal topics, right? Sexuality, body, ingestion, family, friends and leisure, right? So as you can see that, and it's pretty evident from the graph, so the first graph immediately drops off for these topics, and the broader idea that I want to establish is, even after the limit was expanded, all the patterns that were observed in user behavior till 140 character limit those were more or less still observed in the 280 character limit, which is again counterintuitive and sort of defeats the purpose of why Twitter wanted to implement this change. Right. So in to summarize, right, this is evidence indicating that these linguistic signals are generated by similar process for both 140 and 280 character limits. Now let's move on to the second research question, where we want to see, we've already established that people, whenever they are forced to write content in a specific character limit, they cram it up to that point. 140, they cram till 140. If you limit the tweet length to 280, they cram till 280. But does this pattern also change across languages, across geographies, across demographic data, right? So the authors also conducted this analysis across languages, where you observe the largest deviation is for Hindi, Urdu, Persian, Turkish, all these languages. While after the switch happened, a lot of people just started tweeting long form content in these languages. And the interesting thing to note here is, if you see for, let's say, language like Dutch, English, Italian, Spanish, the estimate sort of plateaus down, right? It becomes a bit more consistent or stable after a while. So people have sort of gotten acquainted to the 280 character limit, and they have the anticipated character limit sort of gets stable. But for Hindi or especially Urdu, the graph is still rising. There is a lot more engagement, a lot more content generation and cramming in Hindi, Urdu, Persian and so on, which was again sort of counterintuitive and very interesting to look into how your background, how the linguistic styles and how the different languages that you use to tweet can influence your cramming behavior or behavior on social media, right? So this was another interesting analysis where the authors looked. So now you have data for each language, how much cramming happened in Hindi, let's say, or in English, let's say, before the 140 character limit was expanded and after it was expanded. So this is a very simple plot, just telling you the correlation or the Spearman correlation between the before and after estimates of the amount of cramming that happened across all these languages, right? And as you can see, Hindi and Urdu are right at the top, which is again sort of follows from what we previously saw in the previous slide. And the more cramming there was in a specific language before October 2017, the more cramming that language observed after 2017, even after the cramming limit was sort of relaxed to 280. So again, this is an interesting analysis where, and a bit more mathematically inclined to see how the estimates, so the estimates that we saw, the log normal distributions, the size of runoff and the size of cramming that we were estimating from the log normal distribution, does it change across time and does it change across platforms? So as you can see, again, similar to our previous results, web is more web is the platform where people have the more tendency to tweet more longer form content as compared to mobile. And for example, in the case of mobile devices, right, before the switch was happened, there was only 0.97% chance that tweets would be longer than 140 characters. And even after the switch happened, there was only 1.15% chance that tweets would be longer than 280. But if you look into the web graph, you will see that before the switch happened, there was 3.76% chance. But after it happens, it just jumps off to like 7.77%, which is a huge number. So the second part of the study is that you have how does the hypothetical character limit itself changes dynamically across time periods. So again, for web, as the basic thing that you can see from this slide is, as you go on increasing the character limit on a platform like Twitter, people would have the tendency to cram their content up to that character limit. There is no end to it, as you can see from the web plot, right? But again, pretty consistent results for mobile, where you observe that because mobiles are specifically designed for short form content, you cannot write a longer sort of content like 500 characters or 1000 character limits on mobile. So the evolution of the hypothetical character limit is sort of stable in mobile. So this plot basically tells you, right, if you just see 1%, so what would the plot look like if you want to cram just if you want to get 99% of your tweets in that character limit. And as you can see, mobile is pretty consistent, while web is just constantly increasing, decreasing, right? So as we've already established, right, no matter how one would increase the number of characters, the new limit would again lead to more cramming, and cramming is inherent to how we write language. We've all been sort of given this character limit, answer this question in 80 words, answer this question in 200 words, and we have this tendency to remove some non-functional stop words that we already saw. The semantic style, the syntactic style, all these influence the way we cram and the way we cram content on our platform, right? And the broader context of this study is coming back to what we learned in week 10, right? How a very small change in a platform like Twitter, just expanding 140 to 280 character limit, influences how a user behaves on the platform. And you can see, right, just changing the character limit can influence how a user behaves, and then in turn influence how your data set is scraped and collected. And this sort of manifests into a bias itself that we established. So in conclusion of this study, we saw that there is a need to account for user responses and fluidity in the user behavior, as compared to just, okay, we saw that Twitter expanded the character limit and we just scraped that data. But there is an urgent need for researchers and for practitioners to look into how users also behave with the platform, right? Another very interesting finding that we saw was the bimodal nature of Twitter. Twitter is being used very differently on the web versus on the mobile. On the mobile, it's more of a content consumption thing, and the content that you generate on mobile devices is relatively of lesser length as compared to on web. And as you go on increasing the length character limit, you have the tendency to just write more and more, right? The third part that we saw was tweets closer to the length constraint are generated by very similar syntactic and semantic processes. We saw even after the limit was expanded to 280, both syntactic and semantic patterns in the tweets were very similar. Both 140 and 280 character limits, tweets that were cramming content into both of these limits, they were behaving very similarly for both syntax and semantics. They were talking about the same topics, semantics, and they were removing the same, let's say, stop words or fillers or adjectives instead of, and while keeping the verbs and nouns into the length constraint. Then finally, we also saw how languages also diverge across these user behavior. So what we can already also see, right, that in any analysis that you do on social media data, you can never constrain yourself to just one dimension. So even in this paper, right, we saw multiple dimensions. You have the dimension of web versus mobile, you have the syntax versus semantic dimension, you have the linguistic dimension. Then you can probably expand this study and look into where the user is coming from. If an Indian user living in the United States is tweeting something, how does his linguistic style factor into my length constraint on Twitter, right? So just as a final note, right, how does the future of Twitter look like? Just a few days back, March 21st, Elon Musk tweeted that he's planning to increase the character limit on Twitter to 10,000 now. Along with formatting tools that you see on GitHub, right? The README, Markdown formatting tools. If they come to Twitter, how does that change? So that is another exciting area of research, or very open area of research, that as soon as this change happens, how does this does these findings or do the user behavior changes again after the 10,000 character limit is implemented by Elon Musk in the coming weeks, right? Coming back to the paper, right, the authors also mention the limitations of this work, and the very interesting part to look into here is this study. The authors, I'm quoting the authors mention that this study suffers from limitations, that 1% stream of tweets is known to be susceptible and it can be manipulated very easily. And if you recall a couple weeks back, in the lecture we saw that the sampling API of Twitter can be tampered with, and if you can inject some specific tweets in certain timestamps, you can manipulate what data you are getting in turn, right? So the second part of today's talk will look into a bit more deeper of exactly this phenomenon of how you can tamper with the Twitter API, because Twitter claims that these samples that you scrape from the Twitter API are random, but are they even random? Because as the authors of the current study that we were looking into also mention, the major limitation of this work is that even this 1% dump of stream of tweets is not random. It might be manipulated, it might be biased, and this again leads us to a very important philosophical sort of questions, right? Can we trust these algorithms? Can we trust these platforms which do not disclose how they are sampling their tweets for us to scrape? Can we trust if a Twitter engineer says, right, they are giving us random samples of tweets, can we trust those? So in this current paper, the second part of today's session will look into exactly this. So Twitter does not reveal how data is sampled in their API, right? And if you do any analysis, any research on Twitter API, it becomes an unavoidable black box, but we just run with it because we are under this assumption that Twitter API is very random, and all the results are sort of built on this foundational assumption that Twitter API is giving us random samples. But we need to better understand these platform specific mechanisms and possible biases that can be manifest into your data. And I want to tie this back again to what we saw in week 10, the different kinds of biases, where do these biases come from, how these biases manifest, and what is affected by these biases, right? So again, we are looking into bias at a source in today's session. Both the previous study and this current study is looking into how Twitter itself is biased, how a platform specific change like expanding the character limit influences user behavior. But in the second part of this talk, we are looking into how Twitter as a platform can influence the validity of your research. Instead of how biases manifest, we'll look into how Twitter platform specific changes can affect the validity of your research. We saw that construct validity, external validity, internal validity are very important metrics for us to justify our findings. If your study is not valid enough, no one will take it seriously, and it would not be generalizable to a lot of other findings, right? So this is the paper that we will be talking about in this second part today, tampering with Twitter sample API. Some of the content from this paper more or less were briefly touched upon in week 10, third part week 10, and but yeah, we'll come to the sampling API. We want to focus on Twitter sampling API. So they give us 1% dump of randomly sampled tweets from Twitter. But after this paper was published, the implications of this study were that Twitter immediately changed their stream endpoint, and they implemented some mathematical stuff that we'll come to in the subsequent slides. So what is Twitter API, right? We all know it, we've all used it. Twitter provides its data in three ways. One is the filter API, the other is the sample API, and the third is the REST API. So that we are focusing on Twitter sample API because even the first study that we saw, it focuses on the sample API, the 1% of all tweets randomly sampled worldwide, right? So the current study proposes or investigates the vulnerability of sampling API, and if it is prone to manipulation by external actors or bots or scammers. And if you are doing your analysis, doing your research on a very biased sample, it has the potential to damage the external and all sorts of validities of your scientific research. So in a very high level overview, right, this paper gives you three important specific results that are very important for all social media data researchers and practitioners. First is that it is very easy to tamper data in Twitter sample API. Basically, I can dictate or I can govern what kinds of tweets Twitter will give someone else in their research if they are scraping tweets randomly. So it is not so random anymore, right? The second part is the tampering can manipulate the content and the sentiment of the tweets that another researcher is using, right? So I can manipulate the sentiment of the tweets, I can manipulate what these tweets are talking about, if I can manipulate what tweets are going into this random sample. The third and surprising finding is some groups of users are overrepresented in this sample API. So Twitter claims that it is a truly random 1% sample API, 1% dump of all tweets within a specific time period. But the authors of this paper observe that there are specific users who are overrepresented. So the majority of the tweets are coming from very specific sets of users. So this is the most interesting part of this study, right? The authors were actually able to reverse engineer how a sample API works. So you do a tweet, Twitter automatically assigns the tweet ID to your tweet, right? Which can be represented into a 64-bit representation. Again, 64-bit is like a binary representation based on the numeric digits of your integer 10 base numeric representation. So the authors of the original paper were actually able to convert this tweet ID into 64-bit representations, and what they observed was very surprising. The way that Twitter is handling, or the way that Twitter is sampling what tweet goes into a random sample of this 1% API dump is totally dependent on the timestamp of the tweet. By timestamp, I mean when that tweet was made, when that tweet was sent from my mobile device or my web browser. So this blue part, right, this in this 64-bit representation shows you the 64-bit integer encoding of the timestamp of the tweet, and you can very easily encode this into the milliseconds of the timestamp, right? And the bottom part, right, that you see, this gives you a very high level overview of which timestamp get into the 1% sample. So if you made any tweet, so the Twitter API dump is biased in the sense that all the tweets made in the 657 to 666 millisecond time interval, all those tweets will go into the 1% sample API dump. And then the two other types of APIs, 10% academic sample, 10% enterprise sample, which is a paid endpoint. The authors were also able to reverse engineer those timestamps. But you get the idea, right? This is such a huge risk or bottleneck in the way that we sample these tweets, right? So basically anyone can manipulate what goes into a Twitter API or in whatever data set you download, just based on when I do a tweet, on the timestamp of my tweet. So coming into a bit more mathematical detail, we see that so the TA is equal to TS plus T of delta, where we see TA is the timestamp that when the tweet arrived at the server, right? TA is the time when the tweet arrived at the server, which is equal to the TS, which was your local time at the time of sending to your device. T delta is the latency. So the time, the millisecond time it took from sending the tweet from your mobile device till it happened to reach the Twitter servers. So we already know TA because from the timestamp integer 64-bit representation that we saw. TS we already know from our local mobile device or web browser. So it's very easy for us to look to sort of reverse engineer the T delta, the time it takes for an API to reach a server. So now if we know the time it takes for an API to reach the Twitter servers, we can very easily start tweeting any content that I want to manipulate in a random data dump, so that all of that content just goes into the 1% sample, because now I have all these variables TA, TS and T delta, and I can easily manipulate which specific tweets go into the 1% sample dump and which do not, right? So the authors also say this, the tweets we sent were more likely to arrive at the server within the 1%. So it is still a probabilistic experiment where the tweets that you send at a specific timestamp have just let's say an 80% more chance of getting selected in the selection time window of the 1% sample API, right? So to conduct this experiment, right, the authors created 100 random Twitter accounts and they sent about 21,000 tweets in a series of experiments during the US 2016 elections, like leading up to the Trump versus Hillary Clinton elections in 2016. So the experimental setup sort of looks like this. I think it's pretty self-explanatory, right? Now that you know that any tweet that you do on, let's say, specific timestamp with millistamp precision, that tweet has 80% or a very high chance to get selected in the 1% sample API. So it's very easy for scammers or manipulators to tamper with this sampling API, and in turn or subsequently tamper or hamper all of our research findings or observations that we do in all of our projects, right? So the authors collected around 220 million tweets from the 1% API sample and 2.2 billion tweets from the 10% sample API, again spanning October to November 2016. So this plot I think we've already seen, but this is the major finding from this manipulation experiment, right, that you see. The red part is the tweets that were sent by the authors. These are the manipulated tweets. While the grey part is the normal tweets which were not manipulated. These are totally random from the 1% sample, and the red thick line is what the researchers taking the dump of the sample API 1% would actually be looking into. So if you see like hashtag Trump or hashtag I'm with her for Hillary Clinton, these can be very easily manipulated just because I know which timestamp can actually manipulate the random dump of the API. The second part again is as I was talking about in the previous slide, around 1222 tweets out of the 2000 tweets sent by the authors for hashtag Trump were selected in the sample API 1% dump, which is again very surprising because if it was truly random, only 1% out of those 2000 should have been selected, but it is such an overly large representation of what was actually sent out. This rather small number of tweets were sufficient to sort of quadruple the activity of a hashtag like hashtag Trump, right? And this gives you a very wrong impression of the activity happening on Twitter. If I know and if I'm able to reverse engineer this millisecond timestamp hack, I can manipulate any analysis that you want to do. Let's say you want to conduct an analysis for the upcoming Indian elections, right, 2024, and you want to look into hashtag Modi or hashtag Rahul Gandhi. And if you're using the number of tweets with hashtag Rahul Gandhi as a proxy for number of people interested in Congress or BJP, I can very easily manipulate that sort of stuff, and a political party can gain their hands on research like this and manipulate the Twitter API. So this is very important for us to look into these manipulation experiments as well, so that we can take a look back and in all of the research that we do and look into how we can improve our own methods, right? So again, harkening back to the previous plot, instead of the frequency, now we are also looking into the sentiment. So the authors deliberately sent only positive tweets in the 1222 tweets that were selected in their 1% sample API dump, right? And since I am deliberately posting very positive stuff in the hashtag Trump tweets, the API distribution also, the sentiment distribution in the API dump also gets skewed, and it's very surprising, right? It sort of biases all your analysis, all your construct validity goes for a toss, because if it was truly random, it would have looked something like the bottom line here, but since I've already manipulated this Twitter dump, the positive sentiment of the tweets jumps, and we do not want these sort of manipulation, right? So injecting these tweets with very positive words in the API created a 10-fold increase in the sentiment score, and if we observe these sorts of biases, these can again threaten the validity, external validity of all of our subsequent analysis. So this finishes the first part of the second paper that we are looking into. The second part is, as we've already established, another major finding of this paper was that there are certain accounts which were overrepresented. We've already seen some tweets or some positive sentiment can be manipulated, the frequency of certain hashtags can be manipulated, but let's say you are not manipulating anything, you are just observing the Twitter API dump, and you want to see if the users are totally uniformly distributed, or some users are specifically targeting this API who already know that this API can be manipulated. And so the authors conducted this experiment, very simple experiment, right? So the Twitter imposes a 2400 tweets per day limit on all its users. You cannot post more than 2400 tweets per day, whatever account you may have, even if you have a verified account. And a very easy way for us to look at these suspicious or overrepresented accounts is, if an account has more than like 24 tweets in this 1% sample, because 1% of 2400 tweets per day would be 24, and if someone is deliberately manipulating or tampering with the sample API, they would in this 1% sample term, they would have more than 24 tweets. And to do this mathematically, they just fit a very simple binomial distribution, which gives you the probability that this much amount of people have more than 24 tweets in the dump, right? So the second technique that they use, which is much more statistically significant and much less susceptible to outliers, is entropy. Entropy is again based on the assumption that regular users tweeting at totally random times will create a very uniform millisecond distribution rather than the skewed distributions that we just saw. And non-random tweeting times will skew this distribution that we've already seen, right? So there's a very popular mathematical quantity called Shannon's entropy, which is again defined here, which is just the negative log of probability of someone tweeting at a specific timestamp multiplied by that probability. So the hypothesis that the authors come up with is that if it was totally random, it would be very close to 1, because entropy is based on the definition of randomness, and random tweeting will be very close to 1, and users with entropy, tweeting entropy less than 1, right, or very lower values, will be signaled or will be termed as suspicious accounts. So let's look at what the authors observed. So this is the expected entropy density from the data set that the authors collected, and majority of the users lie in the 0.985 to 1 entropy distribution, and all the values lower than the threshold sort of are termed as the suspicious accounts or overrepresented accounts, because again based on the hypothesis that these accounts are tweeting very frequently, sometimes even beyond the 2400 per day limit given by Twitter, and they are being overrepresented in the 1% Twitter dump, and they may already know about this hack that the authors discovered, the millisecond timestamp hack, and they might be manipulating the Twitter dump. So this is again a very interesting plot. Based on the two mathematical definitions of entropy and binomial distribution, the authors were able to identify the 4 different types of users or accounts which are overrepresented in the 1% sample API dump. So as you can see, the first part is corporate spammer, which on the x-axis you can see, right, which again tweet a lot of times, and the number of days where they are tweeting a lot of times is again more. So it's not by chance that only one day they are tweeting a lot of times, but they are tweeting a lot of times, but this is happening across a lot of days. So these are the corporate spammers. These are the lucky accounts where you can say that probably a random user is tweeting on just 1 or 2 days a lot of tweets. Probably he's attending a workshop or conference, and that's why he's categorized into it. But these are totally organic, real users which were randomly sampled in the 1% dump. The second category is sample cheaters, where they are deliberately tweeting tweets on a lot more days so that they get represented in the 1% sample API at that specific timestamp. And then the in-syncs, we'll come to the definition of in-syncs in a minute, but yeah, let's go at all these 4 categories one by one. So sample cheaters, right, these are the users who are very likely cheaters, right? They tweet a large number of days with more than 48 tweets, and they also show a non-uniform millisecond distribution. So we can hypothesize that these are cheaters who already manipulated the Twitter API sample. And on manual inspection, the authors also found that they link to random websites indicating that these are linking to clickbait titles, clickbait news articles, and so on. So again, as you can see, right, these results just give you a glimpse into how a very specific, a very niche, a very small platform change on Twitter API, how it can have such a huge snowball effect on how spammers work, how users work, how researchers work, and how it can manipulate your data set that you're using. The second part that we see is corporate spammers, where we relatively observed low timestamp irregularities, but there were a lot of days where these guys are tweeting much more than the normal allowed limit of 2400 tweets, right? So on manual inspection, again, the authors found that these are Twitter accounts of companies or products like Amazon, Apple, and so on. And it seems that Twitter allows them specific permissions so that they can exceed those rate limits. Again, they are not sample cheaters, but they are corporate spammers which spam a lot of content, and it gets categorized and it gets overrepresented in your 1% sample. The third category, which is the most interesting here, is the in-syncs, which is the unintentional tampering of the API. So till now we've only seen the API can be intentionally tampered by manipulators, by scammers, by researchers, but there are sometimes also a random user is just tweeting some stuff, right? And just by happenstance or by chance, it just happened that that specific millisecond timestamp is synced with how Twitter sampling API works, that we saw 657 to 666 in that time interval that happened, and that user gets unintentionally overrepresented in the API, right? Because a lot of users and bot accounts on Twitter are periodically tweeting a lot of stuff. We saw an example of a weather bot tweeting the weather of Hyderabad at, let's say, every day or every 10 minutes or every 10 hours, right? So if by chance that millisecond timestamp overlaps with the sample API interval timestamp, so those accounts, those bots will get overrepresented. Conversely, many also miss this millisecond window. So even though they are tweeting much more frequently, but not in the overlapping timestamp, they will not even occur even once in the 1% sample dump. So they sort of essentially become invisible through this lens of sample API. So if you want to get a true picture of Twitter, you won't get it, because it is not truly representative of what Twitter users are, because only very specific users are being sort of coming into the dump of the API that you're downloading, and all the other users, even though they are very active on Twitter, they are not being represented in this sample. So again, this figure we saw in one of the earlier lectures, that you have this bot and just by chance the timestamp does not overlap with the 1% sampling window. It could be that none of your tweets, not even one of your tweets, gets recorded in that 1% sample, while by definition 1% dump of Twitter should have that at least API, right? So again, this is a continuation of these in-sync people, where you see that a statistically sound sampling, right, a truly random sampling would give every tweet from each account on Twitter the same chance of being sampled, which is represented by the horizontal yellow bars, right? So you have time triggered accounts. So each account, at least one of their tweets should be able to have that chance of getting into the 1% dump. But what is happening is exactly the opposite. If you see the vertical blue lines, you will see that only all the tweets or most of the tweets from only 1% of the accounts are being taken into account for the 1% sample API, which is again sort of very platform specific functional bias, and it can threaten the validity of your research. So again, this also shows how decisions related to a system's designs can pollute the integrity of a sample, and a lot of tweets are completely muted from the 1% sample API, which we do not intend to happen, right? So these are called flipped samples, where instead of most of the tweets from all Twitter accounts, Twitter API is giving us the exact opposite, all the tweets from only 1% of the account, which we don't want it to be, right? And we see that it is subject to spammers, but even regularly tweeting bots can be unfortunate enough to never have their tweets selected in the API that we are doing. So the authors also come up with some proposals or solutions of this problem. So one of the interesting solutions that the authors come up with is the problem identified by the authors is that how your Twitter API is sampling these tweets, right? it's completely dependent on the information from the tweet itself. A very straightforward way would instead be to have another random distribution and just sample based on that probability, which is completely independent of how your Twitter information looks like. Another interesting or another content specific sampling method could be hash functions on the text of the tweet. So you can probably then cluster or randomly sample specific hash functions, and those would be hard for spammers to reverse engineer, because hashing is again a huge topic in cryptography. So again, the problem of corporate spamming has this tendency of being tackled if Twitter sort of mark those specific accounts which they have explicitly allowed to exceed the rate limits that we saw, right? Corporate spammers, which Twitter has specifically allowed that, okay, you can tweet more than 2400 times per day. So coming back to the concluding slides and the final discussion, these randoms, while being claimed as random, they are not totally random, right? And these can influence the results and all the inferences that all the researchers or practitioners make based on the data set. So again, if we tie it back to the first study that we saw, based on how users behaved after 140 and 280 character limit, we'll observe that if this data 1% sample itself was biased, all the results or inferences from that original first study that we saw might be biased, and it might not hold ground in a lot of generalizable studies, right? So the authors have finally established that Twitter cannot provide scientifically sound, truly random samples, and it is possible to deliberately influence or tamper with the content of these APIs, and on any topic, right? You can inject very negative tweets about hashtag let's say Samsung Galaxy Note, and if a company is looking into the sentiment of their products online, they would be biased in their results. And these sorts of studies, right, we are looking into these in this session because these are very critical issues that come from doing research with this sort of proprietary data, industry data, where the algorithms are not open source, where the algorithms are not interpretable, and they might constrain your results to methodological or financial resources, right? And hence we must find ways to create truly random samples. Ideally, it should be that these platforms themselves should be providing these samples, but that as we saw from this second study, that is not happening. So we should be able to construct these truly random samples. These studies are a nice step in the right direction, in the sense that they give you a glimpse into how these algorithms, black box algorithms themselves, can be biased, and in turn can sort of threaten the validity of research, like the first study that we saw, where we saw that users have similar behavior if you are giving them the constraint of 140 or 280 characters. Where to go from here, right? Two important findings that I feel all of us should inculcate is that more data is not necessarily better, because as you go on increasing the data sample size, the data size is good for your study, but how that data is sampled is more important than the data size, and that data itself could be biased, right? And are you, based on the results that we saw till now, are you only looking into the behavior of a general population, or is it manipulated by a few people and all your results are based on that? So these are two very important open questions that all of us should look into. And yeah, I think this brings us to the end of today's session. In conclusion, we saw that in the first part of the study, we saw how users' behavior deviates from what Twitter engineers had envisioned users would behave once the 140 character limit was expanded to 280 character limit. In the second study, we saw that studies like the first study, right, their validity can be threatened by how the sampling itself is done at the Twitter servers, and some authors were able to reverse engineer it, and we saw in depth into how the authors were able to do it. And yeah, I think now we can take questions. Are there any questions online?
Any question, Kunal and Harsh?
I have I have just one question, uh, which is what sort of solutions are proposed for the manipulation in the sample API?
Uh,
So, when they were sampling from just a small portion of a second, so how did they what are the solutions that were proposed for countering this bias that was occurring due to the sample API?
so the study that we saw was not proposing or was not removing that bias. It was just giving you that this sample API itself is biased, because no one before them knew that if you are getting a random sample from Twitter, it could be biased. So these authors were able to reverse engineer it, and so some of the solutions that they provide, right? These, I think I added them in the slides. One of the solution is that you can have, instead of relying on the Twitter timestamp, you can rely on the hash functions of the content of the tweet, or just have a totally random binomial distribution and use that to sample tweets from your Twitter API, because that is not dependent on when your tweet was sent to the Twitter server, which we saw. If that is the case, people or scammers can bias your results.
Okay, and did after what impact did this have on Twitter? Were there any changes in their API after this?
Yeah, so I think we had a slide in the earlier parts. Immediately after this paper was published, right? Twitter's lead API engineer actually posted on the Twitter forum that they have completely removed the sampling API method and they are coming up with a new stream endpoint. It's dated October 2018. This study was published somewhere in 2017, and so Twitter now again it's a black box, right? Till someone reverse engineers that new API sampling endpoint, it probably is hard for us to guess. But based on recent studies, people have been able to see that now Twitter is not relying on just one time interval of the API. Twitter has now constructed a uniformly distributed time interval. So that sort of gives you a better chance of occurring in the 1% sample dump. And yeah, implications, Twitter just completely removed how they previously used to sample APIs, and they came up with a new algorithm. That is the major implication, and hence all the results that you see after 2018, 2019 published, they are much more reliable or generalizable as compared to the studies published before.
Okay, that's all from my side. Thank you.
Okay, thank you.